We must find inspiration or risk the continuation of civilization. This emotive force powers our progress and is distilled from a variety of sources. The James Webb Space Telescope was built to take us back in time, but what it can tell us about ourselves may determine our future. The observatory's story shows us that we need not fear doing really big things. The Webb telescope, named after former NASA administrator James Webb, is a near-infrared space telescope currently in orbit around the Sun, 1.5 million kilometers from Earth. The primary purpose of Webb is to study the beginning of everything, or at least as far back as we can see in time. This is possible because light has a fixed maximum speed in space, and space is very, very big. So vast that we measure it in the time it takes from light to get from one place to another. The sun you feel on your skin left the surface of our star 8 minutes ago. Our galaxy, the Milky Way, is about 100,000 light years across. Webb is looking for things 13.5 billion years away. One of my favorite quotes is, "Given enough time, hydrogen begins to wonder where it came from and where it is going." With Webb, we would look to the beginnings of what made it possible for us to be. So how will it do this? In the last episode, we talked about turning theory into facts. One theory is that you can determine what atoms or molecules you are looking at by analyzing individual parts of the light from those objects. The earliest experiments with separating light happened as far back as the Romans, using a prism to generate a rainbow of colors. In 1814, Joseph von Fraunhofer, using prisms and more precise optical elements, built the first true spectroscope. When light was passed through it, he saw these lines. The crucial part is that the lines were different depending on the light source. He of course pointed his device at the sun and discovered 574 dark lines, though he did not know what they meant. He also saw dark lines from several bright stars. Importantly, the pattern of lines were different from the sun and other stars. What he could not know then is that he was seeing absorption lines. Different elements absorb different wavelengths of light in narrow bands. The pattern of the lines is always the same for the same substance. Hydrogen, for example, has these absorption lines and allows all other light to pass through. This feature of nature became very useful during the eclipse of 1868. Pierre Janssen traveled to Guntur, India to observe it and brought along a spectroscope. He noticed this line. It was a mystery, as it did not correspond to anything known at that time. Later that year in London, Sir Joseph Norman Lockyer also observed the line. He proposed that it was an unknown element. Since it was found in the sun, he named it after the Greek god of the sun, Helios. That is how the element helium was discovered. With this tool, scientists have been able to document tens of thousands of spectral lines and what they should be. One neat feature of distant objects in space is that the light they emit is shifted to the red. This is called redshift. The further away an object, the more redshift it has. By comparing the spectral lines created in the lab to what we see in the sky, we can determine the age and distance of stars and galaxies billions of years old and billions of light years away. Telescopes on the ground have to look through the atmosphere, and optical ones can only see at night. Putting one in space is a great idea. It can observe all the time without obstructions like clouds. But that is hard. It has to be strong enough to survive the flight, light enough to be able to fly, tough enough to withstand years in space, be able to power itself, collect and transmit the data, and we can't really make quick repairs if something goes wrong. It is an order of magnitude harder than building and operating a telescope on the ground. It is a good thing humans like doing very hard things. The Hubble Space Telescope was launched on April 24th, 1990. After a servicing trip with the space shuttle to correct for some slight blurriness in December 93, Hubble started returning images like this. This is the Hubble Deep Field. Almost 3,000 galaxies are in this one image. Hubble sees mostly the same light that we can see. In order to see back in time even further, longer wavelengths are better, infrared wavelengths. It was clear the successor to the Hubble would be a telescope of this kind, and in 1996 the program officially started, called, creatively, the Next Generation Space Telescope. In order to observe infrared as accurately as possible, it would need to be very cold and isolated from heat sources like the sun and Earth. Therefore, it would need to be in an orbit around the sun about 1.5 million kilometers away. No servicing missions like with Hubble. The engineering challenge lay in designing a precise space telescope and then folding it up so that it could fit into a rocket fairing. The primary mirror is 6.5 meters or 2.7 times the size of Hubble's. It is made up of 18 segments of gold-coated beryllium that can be individually focused. A giant 5-layer heat shield made out of Kapton was built to protect Webb from the sun. Overall, it would have 344 single-point failures. That is, if any of the 344 procedures to deploy Webb failed, So would the mission. From 1996 onward, Webb survived multiple administrations, budget cuts, design changes, and technical challenges. The project was the result of over 25 years, $10 billion, and countless hours of work from tens of thousands of humans. With international partnerships between NASA, the European Space Agency, and Canadian Space Agency, 250 companies, and 50 universities across 14 countries. Finally, it had come time to risk it all to peek just a little bit more beyond the veil. On December 25th, 2021, the observatory launched into the heavens. The Webb was now on its own. Over the next 29 days, Webb would undergo a metamorphosis. 178 release mechanisms would need to operate flawlessly to avoid over 300 single-point failures. Should this be the last act of the endeavor, the science will be delayed, but not extinguished. The inspiration machine would drift in space, unable to directly support knowledge, but would rather be a pathfinder for our next attempt at a really big thing. For the Webb, that would not be its fate. All procedures were successful, and the telescope entered into a stable orbit, ready to extend our understanding. In July 2022, the first images were released. With the infrared spectroscopy powers of Webb, we were able to see hundreds of millions of years farther back in time. Using theory built from light passing through prisms in the 1800s to the facts of spectral lines, we created a machine to apply all our collective scientific knowledge to look back in time 13.5 billion years and search for direct evidence of habitable worlds beyond our own. And that is the next step, applying tested facts in new areas to expand the available sphere of knowledge. Webb is an example of this process. It's been said that it opened up a new sky for astronomy. It was also built to inspire. These images create feelings of wonder and awe. How fortunate we are to have our perfect world floating through the vastness of space. It also inspires in another way, that we can solve very big problems. Each time we learn, it reinforces that we can learn, and that big problems are solvable. With enough imagination and tenacity, the future is what we make it. To help Aletheion continue to explore, please like and subscribe. We also have a Patreon for those that may be inclined. And if you'd like to add to the discussion, please join us in the Discord. Links below.